Okay, so first things first, let's look on the configuration. In this specific scenario, we have a configuration of classic 5G network, which is consists of FR1 frequency cells. We have 13 sites deployed in the city center of Dublin. As you can see, Liffey River here in the middle. And we have on every of these 13 sites 2 pointing sectors. They are all using massive MIMO dense urban analog beamforming technology. So we have sectors pointing north, west, and northeast on each of those sides, and color-wise, we can see that they are red and green. So these cells basically belong to FR1. Additionally, we have the FR3 cells, which are 6G cells in FR3 7 gigahertz central frequency. The difference between those bands are that the FR1 bands, they are usually, because they are lower frequency, they're 2.7 gigahertz, they have better propagation capabilities, RF propagation, and for that reason, they will have much better signal compared to the FR3 frequency. But the limitation is that the FR1 frequency have much less bandwidth. They, in this configuration, they have only 70 megahertz bandwidth, as compared to the FR3 cells, that each of the cells has the bandwidth of between 200 to 400 megahertz. So that means at least 3 times and sometimes more resources on each of the cells. However, the propagation of the FR3 frequency is much lower, and for that reason, especially for the indoor users, they will be challenged to use the FR3 frequency. And also, once you're getting away farther from the cell, it might be that you will get out of the coverage. For that reason, you need cognitive AI-based application to manage the traffic steering decisions between the FR1 to FR3 frequencies. And in this specific simulation, basically what we will see, we will randomly distribute the users between different frequencies, and we will let users move between different frequencies based on 3GPP deterministic decisions based on basically handovers. And we will see that basically these deterministic 3GPP decisions are not enough, because if we really want to benefit the bandwidth, we really want to optimize the spectral efficiency, we need to use the intelligent app, and I will show some examples. But also what we will see is that during this presentation, how the FR3 frequency can potentially unlock the improvement of the UE user quality of service and UE experience in the network, because it has much higher bandwidth, and because it can serve basically as additional capacity boost to the legacy FR1 5G frequencies. Okay, so once we understand the setup, let's now see the results of the simulation and see how the FR3 frequency impacts the UE throughput and the UE RSRP and the UE behavior overall in the simulation, and the network quality perception of the UEs. So this is the initial picture. What we see here, first of all, we assign several services and several UE groups. We can see here that we have pedestrians, we have cars, we have buses, and we have also indoor UEs that are inside the building. As I mentioned previously, the simulation all is done in the real GIS map in Dublin city center. So the cars and the buses will be moving, and also the pedestrians will be moving along the streets, and the indoor users will be inside of the predefined building that we have in Dublin building layer. So that's already a very significant step towards the Run Digital Twin, where we actually use the realistic data from the real maps in our simulations. Okay. So what will basically happen that by introducing so many different type of UEs and using both the voice services and the EMBB services such as video buffer, that we basically each of the UEs here, when we have 60 cars and all of them, they want to achieve 50 megabits per second. So we put a big demand on the resources, and we will see how basically the network will tackle those high demands and which UEs will suffer, and how the FR3 frequency will allow offload of the traffic and solve the problems. The simulation, I ran it before in background to save time, so we'll just look at the some results and see what are the conclusions. So let's go to the live charts here. So first of all, I wanted to mention that obviously, as we expect, the FR3 should have lower coverage compared to FR1. So let's randomly choose here some of the FR1 cells, and let's see how their coverage is compared to the FR2. So for example, let's choose this S1 cell pointing northwest, FR1 cell 1, and let's see the propagation here. So this is basically this cell over here, and you see on the left corner we have basically a very dark purple colors. That means that basically this cell has quite a good coverage in this northwest corner, that where this cell is pointing. And of course this is massive MIMO, so this is not a shape. You can see that there are basically several beams there. There are several beams that they are in a deeper dark color. So if we want, for example, to compare with the FR3, so let's choose equivalent FR3 cell, and this would be, for example, this one. So this cell is actually pointing to northeast because this is cell 1. Actually, if we choose the cell 2, it will be pointing to the other direction, and cell 3 is pointing more or less in this direction, which is west. So you also see that there are like a dark colors, but they are much less darker than the previous FR1. And that is very expected, because that means that basically FR3 frequency being 7.2 GHz central frequency, they have less robust propagation, RF propagation, and for that reason that means this frequency will not be suitable for every UE. Otherwise we would prefer to camp always to use only the FR3. But the downside of the FR3 that because of the high central frequency, the propagation, so it's only good for the cells that are really close to the pole, to the base station. The indoor users or the users that are far from the cell, they will not be able to use the FR3. So ideally, the intelligent application will put all the users that are resource consuming and they're close to the cell, it will put it on FR3, and the ones that are indoors and outside, they should probably be on FR1. So this is something that intelligent cognitive app should do in order to optimize the usage of the resources. Now, running it in the 3GPP way with deterministic thresholds, let's see what happened. So let's select one of the UEs and see how it behaves. So if I choose, for example, one of the cars, this will be car 35, for example. So let's look on one moment on the car throughput over here. So there are jumps, first of all, and there are many handovers. So let's investigate a little bit. So if we look on the first handover here, we see here that it's handovers from FR1 to FR3. And the moment that handover is happening, look what's happening to the throughput. So the demand throughput is on the green dotted line here. You can see is 50 megabits per second. This is the demand throughput. Of course, we never reach the demand throughput because this is there is enough resources. But with FR3 here, when we hand over to the FR3, we are very close. We are basically 45 megabits here, which is very close to the demand throughput. But when we are handover to the here back again from FR3 to FR1, we are getting much. So the throughput is jumping because of the lack of the resources and also much lower throughput. But then the question is why this handover is still happening. And this handover is happening because our decision of the handover based on the RSRP threshold only. And when the RSRP threshold is becoming stronger, that means that we jump immediately to FR1. And this is regardless what will be the performance in this frequency. And for that reason, this is something that if we would do it intelligently with intelligent cognitive traffic steering app, then it might be that in spite that the RSRP and sometimes even RSRQ is lower, it might be that because we have the FR3 frequency, which has much more PRBs, it has 200 to 400 megahertz bandwidth, so basically 3 to 4 times to even sometimes 5 times more PRBs compared to FR1. It might be that we need to delay this handover and still make this UE stay on the FR3 and benefit the higher throughput and not fight for the resources in already overloaded FR1. By the way, let's see what's happening at this moment if you look on the cell level. So let's look now on this FR1 northeast cell 1. So let's choose here S4 FR1 north. So this is this cell, FR1 northeast cell 1. Am I right? Yes. And let's look on, so we can see here the statistics, what is happening with this cell. So as we can see, in terms of PRB utilization, this is basically this yellowish line. This is overloaded cell because it's almost all the time uses 100% of the PRBs. So of course, if after 1 minute when we see already the PRBs is on the 100% and we make a handover to this cell where there is already a lack of PRBs, that's not a very intelligent decision, and for that reason we see that the throughput is not satisfied. But on the other hand, if we look on this cell, for example, that is the throughput was very good, S5 FR3 C1. So let's look on this cell, S5 FR3 C1. This is this one. So look what's happening. So this cell is much more free. So look the PRB utilization, and this handover happened in 30 seconds. So you see before 30 seconds, the PRB utilization here was only the PRB utilization here was only 21%. And then handover happened. We hand over this car 35. So the PRB utilization jumped towards 42%. So that's because of the handover. And look, the experience of the UE, it's almost reaching the demand throughput. So it's really, really good. So that was a good decision. But unfortunately, after 30 seconds, we hand over back to the FR1 and then the throughput degraded again. So that's where emphasizes the need for intelligent decision in order to steer the traffic in the intelligent way and not only in the deterministic way where we only look on the propagation of the RSRP and RSRQ. Right? Maybe let's look on another example. Let's take, for example, bus number, one of the buses, say bus number 93. So what happened here? So the bus, it actually has lower ambition. It only wants to reach 20 megabits per second. So here it was using the FR3, and at some point it handover from FR3 to FR1. And here you see, because the difference, we ask for less throughput. So the difference is not as big as we saw in the car, because cars are demanding much higher throughput. But still we see the difference in performance. Once we jump to FR1, even though the signal is stronger, but the performance is worse. And here we jump back again from from site 4, cell 1, FR1 to FR3, and we see jump again in the throughput. And every time it is happening, right? Every time it is happening when we jump to FR3, the throughput is becoming better. Here we go, look what's happening. We go back to the FR1, and here we even starting to get very poor performance, because probably this FR1 is being overutilized, and then we cannot satisfy the throughput. But the signal is still good. That means we are not handovering to the FR3. So again, this is suboptimal because we are not using intelligence, we are not using cognitive apps, we're just using deterministic approach. But then I want to show you the opposite example. It's not always that we can say the FR3 is better, because, for example, for indoor UEs, it could be the opposite. So let's choose one of the indoor UEs example. Indoor here is a good example, because here look what is happening. We are on the FR3 and we are changing the FR1, and look what is happening to the throughput. The throughput is actually improving, is jumping when we are, because this is the indoor UE, and you remember what I told you about the indoor UEs. The FR3 is very bad for indoor UEs because the propagation is very low, so the signal is very low. So even though we have a lot of resources on the FR3, but for indoor UEs, when you jump to the FR1, actually, because the propagation is much better, in some cases it's still better to be on the FR1. And here is a good example. We were on the FR3, we were having all very low throughput because the propagation is very low, and then we jumped to the FR1 and the throughput improved. So that's all. Basically, the conclusion from this is that AI run scenario generator allows you to simulate new technology, FR3, boost of the capacity layer, and allows you to test and train your AI traffic steering and quality of service aware apps in order to manage the user experience in a more cognitive and more intelligent way. And this is your way basically to utilize this technology to train your AI model, to test your apps, and to achieve better performance using the AI run scenario generators. Thank you for watching this demo. Hope you like this, and see you in the next demo.